Okay, so I'm going to state the algorithm for solving this integer programming. But first, let me just show you the animation from last time because I had fixed it throughout the class, so just so that you can see the correct version like all at once. So this is like the idea for the algorithm. So uh, okay, we had like some inequalities and the region that it had given us was this. So just to remind your as a reminder, the idea is like the way we're going to solve the problem, if you're looking for solutions where all the coordinates are integer, is just let's just pretend that for a moment that that's not the case. So you just treat the problem as a regular optimization problem, dropping the condition that the coordinates must be integers. Last time, if you remember, the function was x plus y, so just the sum of the two coordinates. So in that case, the max is very easy to identify in this point. It's just like the top of the top corner of this polyhedron. Okay, so this is where the max occurs. But if you look at the coordinates, actually I have them like here. Um, like both coordinates are fraction. I mean, not fractional, but they have like they're not integer, right? So what the branch and bound method does is that you kind of like choose one of the two coordinates. And again, there like if you are interested in this, like there's a lot of literature. So obviously there are more efficient ways of doing it. For us, kind of would be almost like random how we do it. So you choose one of the two coordinates to begin with. So let's say you choose like the first one, 2.67. Okay. Um, so what I'm going to do is kind of like remove the region. So to like the closest integers to 2.67 are 2 and 3, right? So I'll kind of remove the region in the polyhedron where x is between 2 and 3, which gives you as a leftover these two things, right? Let me move this around. Okay, so that is what remains. If you kind of, which is kind of like some sort of a strip, but if you remove those two values, then that's like the values of x between 2 and 3, you kind of like get those two regions instead. Okay, and then again, you kind of pretend that you don't care about the integer condition, and you try to find the max on each of the separate regions. Okay, so the maxes for each separate region is are these two. Okay, because again, we're just like the function was just the sum of the first two coordinates. Um, of these two maxes, of these 2 points, you just keep the one that gives you the largest value for the max. Okay, so of these two, like it is the one on the right that has a larger value. So I'll totally forget about this second region. Okay. And again, you do it for practical reasons because the idea of this method is to subdivide, subdivide, subdivide. If you keep track of all the branches, this is kind of grows exponentially. And, because multiply by 2 and you very quickly get to very large numbers. So you kind of, even though this won't necessarily guarantee that you find the best point available, but it will guarantee that it will be a local max, which is good enough for like these problems. Like in fact, integer programming, which is what I was telling you last time, is a way more complicated problem in terms of computer science and like complexity theory. If they have ways to analyze how hard like a problem is to solve on a computer, and so, but yeah, you just realistically have to keep just one branch because otherwise, if you keep track of all of them, like the problem becomes exponentially long. Um, and so, okay, so now in this branch, okay, so again, the point was 3.3 comma 3.5. So now the only coordinate that has an issue is that the y coordinate, okay? And then the two integer values which are closest to 3.5 are 3 and 4, right? So kind of like the idea is to remove the region from between 3 and 4 from the region that we have here. So I think you should get this. Okay. So you keep the green one because that is where like the values for like are outside kind of like this forbidden zone. Okay. Oh, just forget about the triangle again. Okay. And here you have to find as as be, as before, you find the point with the largest value for the function, which is x plus y. So the point with the largest value for the function, it happens to be here. But this point, again, is now fractional or non-integer in the first coordinate. So notice that sometimes it swaps, right? Like it's not that just because it was integer at one point, like it cannot revert back to being like non-integer. So like, because so you have to kind of like just keep track of everything. So now 3.25, the integers that are closest to it are 3 and 4, right? So you kind of remove the region between 3 and 4 from here, okay? So let me see. Okay, so if you remove the region between 3 and 4, you will get something like this. Where are you? Where's the other one? Actually, that should be a triangle. So oh my God, there's so many. Like, let me put the triangle here for a second. Not to make a mistake. Ha, sorry, I dropped that triangle. So this is what you get if you just look at the stuff between 3 and 4. And then you get two potential points, you know. You get two potential points, like because you got two regions, and then you just keep again, you keep the one that gives you the largest value, which happens to be because of the function was just the sum of the two coordinates. Let's see. This is 4 and 1.5 that adds to 5.5, and this one was 3 and 3, which adds up to 6. So this one has like a slightly bigger value for the function. So you keep that value, and so you keep that region. But if you see that one, so let me remove this one again. So this one is no longer important. So let me remove it. Okay. And then, I mean, this is already good to go because this is already a point with two integer values, and then you're done. So the local max that we find here with the branch and bound method was 3,3. So you see, like, if you go through the colors, you see the process. Like, if we started with one candidate, it branches into two. You keep the one with this red point, then you keep like you find the green one, and then it branches again into two, and then you keep the largest one. So there's branching, 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 and then like you kind of you keep track of the largest one. In practice, I would ask you to do this graphically because like in theory you would apply the simplex method to each of them, but like it's not realistic, for us. So it's kind of like I would expect you to just solve it graphically. For like you draw the region on the plane and then cut, 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 and then you would get the answer. Is that making sense? Kind of like the idea behind it. Like it's fun but tedious, because again you subdivide, subdivide, subdivide. So let me write it as like an algorithm of sorts. Although like kind of like the picture kind of like is more clear than what the algorithm will say, but like I still will let me put it. So let me again repeat what the branch and bound method says. I'll try to kind of to write it as an algorithm, like what you would like if you had to program it, this how you would write it down. So again, the goal is to solve the max of c dot x subject to x greater or equal to 0, ax less or equal to b. Those are the usual conditions, but the extra requirement is that the vector has like each entry, each coordinate is an integer, right? Each variable is very integer. Let's just say each xi is an integer. Right, where you think of x as being x1, x2, up to xn. Okay, so here are the steps. So step one, which is called the relaxation. Because the idea is you are going to make the problem easier to solve. That's what you mean by relaxation in this context. So to relax the problem, you just solve the problem without the integer conditions. So you drop the integer conditions to use the simplex method if you needed it. So solve the problem, dropping the integer conditions. So the usual one, okay? Okay. So this is like the relaxation. So step two called x, like let's call this again, like writing it is a way more tedious than like in practice how it's done. But step two, let's call x star the max that you find. Call x star the vector that maximizes the function. So c dot x. If all the entries are if all the entries for this vector are integers, they're good to go. Algorithm stops, right? So if all the entries are integers, you stop and you're done. Otherwise, again, what does it mean if the vector is not full of integer values? It means that one of the values for the coordinates has to be non-integer. So otherwise, one of its coordinates has a non-integer value, which I'll write. So let's say that that coordinate is xi. Say it is xi. And because it's not an integer, that means that it is like 3.5 or 4.2. So it means that it is an integer plus some number between 0 and 1, right? So, and write it as where n is an integer, n is an integer, and f is like the fractional part, right? Which is like a number between 0 and 1. So like the fractional part is, 0.5, 0.3, 0.1, whatever it ends up being. Setup so far so good, everyone with me, like the setup. Okay, and then basically we do what I was showing you on the animation. You kind of like add as an extra condition, kind of like you branch the problem into two, one where like the values that you're looking for are less than n, and the other branch where the values are greater than n plus one. So kind of like bifurcate the problem into two separate optimization problems. So then solve instead two problems. So this is kind of like the branching part. So this is where the branching occurs, right? So So the first branch is where you are asking as an extra condition that this variable has to be less or equal to n. And the other branch is where you ask the extra condition that the variable is greater or equal to n plus one. So it's kind of like the removing the strip where like the coordinate is like could have been not an integer. So and max. So let's call this branch one and branch two. And let's say that branch one produces a max, produces a solution, which I'll call x1 because it's in the first branch. And let's say that this one produces a solution, which I'll call x2 star. And then kind of what happens is that of the two, you continue on the branch that gives you the highest value for the function, the largest value, and then you and then you drop the previous branch. Okay. So let's call, what would this be? Step 3, maybe. Step 3 is that you use the branch which yields the largest value for the function. And repeat the algorithm until all the coordinates, and you redo the steps if like one of the coordinates of this max is not integer, so you have to stop until all the coordinates are integers. And you repeat the steps if the solution had a non-integer coordinate. Okay. That making sense? And as I remark, as I was saying, this method does not guarantee that you would find the best possible max, like the value, like the largest max. I mean, that sounds weird. It doesn't guarantee that the vector that you find would have given you the largest value among all the possible candidates. It's just kind of like within the branch, it would have been the best one, so because I think someone had asked me last time this, like, it is possible that in the branch that you threw out, in the next step, that one does not decrease as much as like the decrease in the value of the function in the other branches. Because remember, like, the idea is that in each branch, like, let me write this down. Each, as you branch, like, the region that you're working with shrinks. And when you shrink the region, the max can only go down. I mean, it could stay the same, but it can never increase. So just as a remark, as you do the branches, the region shrinks. So the max can never go up, right? So the max can't increase. So the max you find in each branch on each branch can't increase. It only goes down. Goes down or remains the same. Yes.
So it's possible the brain to choose the region that doesn't contain the max.
Right. Oh, totally. Yeah. It would have been, and yeah, no, definitely. Yeah, it's not, and again, like, there are like algorithms to try to kind of like first, like, what that also says is that you want to branch out ideally in as little steps as possible, because every time you branch, you kind of like run the risk of decreasing the value of the function. So then they're like, yeah, like, then again, this is kind of like the $1 million question, literally, because it saves millions of dollars to the companies, right? Like, or billions, like, depending on how large your company is. But of course, you want the algorithms to terminate as fast as possible, and also to be like, give you like the closest value to the actual max as possible. So there is all this technology, or like this, like, literature about, oh, like, for example, like, here I had said, like, imagine you had to choose, like, three coordinates were non-integer, right? Which one do you choose to start the branching? Like, there is a way to kind of like think about which is like a better strategy than others, right? But then but that is kind of getting too much into the weeds of what we want to do. Like, kind of like the point of this is like, oh, by the way, there's this thing called the branch method. And if you ever need to use it, then you know that that's what you need to Google. And then you kind of like read more like carefully what like all the details. But this is like very long literature, because it's like as I was saying, like, in practice, integer optimization is really what people use the most, because you cannot produce a fractional, you cannot produce like 2.5 Nintendos, like Wii's, like, like, everything has to be integer at the end for most realistic things. So like linear programs are used mostly to solve this branching stuff. um and so definitely, like, the efficiency, and there are all these other questions of how to make this like actually not like, don't, so that it doesn't result in an answer that is too far away from the best one you could have like obtained. But yeah, like, that is like a like long topic. But yeah, like, so definitely there's a lot of like freedom on how we're setting things up, but you can then try to narrow it down. So, like, if try to, you know kind of guarantee that most of the examples, or most of the time, it gives you like kind of like close to ideal. But yeah, in general, it would be kind of like a local max. That's how would you call it, because it's kind of like only within the branch that you end up finishing. Like, that would have been the best, but not in all the others that you are killing off. Like, who knows? I mean, that there you do have to understand a lot better, like the function, and the region, and all this other stuff. But yeah, let me say that. So it only guarantees this method. So this method only guarantees um a local max. And by that I mean like a max in the branches, within the branches that you chose, within the branches that you keep.
Um, very run pretty high risk of finding something that.
Yeah, no, and I mean, I'm sure, like, it's kind of like this thing, like where in theory everything kind of can be sound terrible, but in practice, sometimes it's kind of like, it's the same thing with the simplex method, where like when it was found at the beginning, no one would think that it would work as good as it worked, like in terms of like running time for the polynomial, like how much time it ended up taking to computer, like to do on the computer. So I don't know, like, since I have never really done this in practice, I don't know really how much of an issue. It theoretically it's a monster, but I don't know how much of an issue it ends up being in practice. It could be a lot less worse than you would expect theoretically. Um, so, but yeah, it's kind of like this is what people call like operations research and all this stuff. I believe, like kind of like this area that works with all like make like understanding very well the details here. So in practice, like sometimes in theory things can go awfully wrong, but in practice, it's maybe you're looking on all the types of problems people happen to work in. They just happen to not be as bad as you would have expected, and that sometimes like does occur, and that's great. But they're like famous, like their problems are famously hard and things like that. And the book does mention some of them, but it's kind of like interesting, like to kind of like see like what fixes there are. But for that, you do need to kind of like look at a book, like an actual like more advanced book on optimization and all this stuff, like where like they do this kind of like a couple of chapters on how to do this properly. Like taking into account all those like uh, potential issues. That's what I mean. Okay. Just to show you just to show you how the branches look like diagrammatically in the example we were doing. Um, and then I'll give you like an application to these perfect matching problems, which are kind of fun. Um, The thing with linear optimization, it is that it is insane how many applications it has. Like it probably is like the class that you will ever see that has the most applications. So it is like a never-ending list of like things that you can use it for. So and really like the difficulty a lot of the time is just how do you set up the correct linear optimization problem. Everything will be solved by the simplex method or a variation of. Like there's now other things like interior points, ellipsoid methods, like which of the book mentions, by the way. But all that I'm saying is that it kind of like, where you would get paid for is like, oh, like, how do you find the optimization model? And then, yeah, like the people who are like focused on like making the algorithms more efficient. But, like it does take a lot of creativity to kind of like set it up the right way. You know, so that you have like a good model to work with. So, okay, yeah. So in our example, just to kind of like show how like in our example how the branches look like, where the function was z was the function, it was x1 plus x2. This was our function. So we had like like the 0th branch, which was like the first max. Which is roughly 2.67. That's what I showed you on GeoGebra. 4.16. Okay, so that is what you find just by doing the linear optimization problem. So this is like the linear optimization. So step 1. Okay, and then like what I did was to branch. I branched on this condition, right? Since it's 2.67, the branches that I do are one where well, let's call it x1, where x1 is less than 2, and the other branch that I did is where x1 is greater or equal to 3. Okay, that was like the branching that happened. And then if you do it this way, the max that, or like the candidate for the max that you happen to find here um, was 2 comma 3.5. Okay, and the value of the function here would have been like 5.5. And if with the other condition, it would, the max that you found was 3.5, which if you remember, those were the red dots on the animation that I had. Okay, and the value for the max, because it's just the sum of the coordinates, is 6.5 here. Okay, let me put that. And so the idea is that, of the two branches, you just keep the one with the largest value. So I keep the second branch. And then there's only one possibility, which is to branch at the second coordinate, because the first one is already an integer. So you branch there. So the branching would have required x2 greater or equal to 4 or x2 less or equal to 3. Now, the thing is, like, in this picture, if you remember the picture, once you are here, there's nothing, like, kind of like that's empty region. There's no, there was nothing like there, like above 4. So this is kind of like an empty region. So you can stop. You don't have to worry about this sub case. But in other situations, like there could have still been something there. And so if you kind of like added that condition, then the x star that you find was 3.25 and 3. Let me see, just to double check. Is this one, right? 3.25 and 3, perfect. So, and so there, well, there's nothing to choose, because there's only one branch that survived here, because the other one was empty. But still, now you having to run into this problem where now this one turned again into a non-integer. So you have to branch again here. And again, the branching occurs by asking x1 to be greater or equal to 4 and x1 to be less or equal to 3. Okay. And if you do that, then on this side of the branch, you get 3, 3, which gives you a value for 6 for the function. And on this side, you got 1.5, which gives you a value for the function of 5.5. So clearly, you keep this one, and all the coordinates are integers. So this is like the winner, because if you kept branching, which doesn't make sense in this case, but if you had kept branching, then you run the risk of lowering the value of the function. So once you are done, like, once you have something with integer coordinates, that's perfect, because branching more for whatever reason would only run the risk of like decreasing the coordinates, the value for the max. So, you want to again, like kind of like in an ideal world, you would like to terminate as fast as possible, And kind of like the way of the branches is that you have to think that, like the conditions accumulate. So in this step, like in the purple step, you are still considering that x1 was already greater or equal to 3. You see? So like this final step incorporates all the conditions that were like, if you were to solve it as an optimization problem, like in the simplex method, which I won't ask you because it would take forever, but we're doing graphically. But if you were to put it in the optimization as a simplex method, so for the blue one, you would have to add as an equality this one and this one. So like the inequalities accumulate that you had to be adding. But it's kind of cute, like it's got like a fun process. Uh, is that making sense? Okay, so just to give you this application to the perfect matching, because it's also like an interesting type of problem, and it's connected to this integer programming. So So I think I had like told you a little bit about that next last time, but I'll kind of remind you what the motivation is. So again, it's always nice to start with small cases, so just to see what the idea behind it is. But let's say just you have three people. I'll just go alphabetically. So Alice, Bob, and Charles. So Alice. So ABC basically. So you have three people and you want so there are different ways to motivate it. One way to motivate it is that maybe they work at the same company and then you have to give a position to each of them, and so you want, to kind of like do it in such a way that maximizes, kind of like what you expect the company, like the kind of like their qualifications fit the potential job as much as possible. But just to make it more concrete, like imagine you have three types of movies that you could sell to them. So like of different genres. So like like you have like a drama movie, a horror movie, you know, and a sci-fi movie. So it's important here that they're kind of like two types of things and they're the same number of each category. So there are three people and three movies. It could be like usually people like like, or it could be 10 cities and 10 truck and 10 cars, like if you thought about it kind of like a network where you're ship, like you have to decide which truck will transport like material to like products to a particular city. So I'll kind of like write the conditions in a moment, but the idea is like there, you know it is what you would call like a graph, and they kind of like the nodes, which is, or the vertices, which are like the circles that I'm drawing, kind of like is split into two categories, and there's as like each has like the same number of elements. And then I'll draw like an edge. I'll draw an edge if they like the person is willing to buy the movie from me. Okay. So for example, just to make it you know So in this case, the way I'm interpreting these edges is that Alice is willing, she's fine buying the movie from each of the genres, and A1, A2, A3 is like the amount of money she's willing to pay for each particular one. Okay. But for example, Bob is only interested in drama and horror, so he won't accept like me trying to sell him like the sci-fi movie. Okay. He just refuses to. And again, like for drama and horror, he's willing to pay B1, B2 dollars. Okay. And then just to, let's say also Charles has a preference with sci-fi and horror. And so that is like the amount that he would be willing to pay for those two, but he wouldn't accept one from drama. Okay. And again, there like you could imagine all the variations you could think about. Maybe all of them are willing to accept any of the categories, et cetera, right? But kind of like the goal from your perspective, if you know that those are kind of like the prices they're willing to pay, is that you want to like sell the product, like the corresponding movie to like each person, so that you end up with the most amount of money, at the end, right? So like it's kind of like an assignment problem. How should I like assign the movies so that I maximize the money that I make. Okay. So like the idea is like kind of like in the end, you know, um, the goal. So like, in the end, like in the end, this could be like a potential configuration. Like, you could end up with Alice, Bob, and Charles. Okay, so ABC, I'll just call them ABC. Then this is drama, horror, sci-fi. So let's call S for sci-fi. So in the end, it could be that the solution is that, Alice got the drama where she paid A1, that Bob, you know, he would, like, in that case, he would have like received the horror, like, well, let's do one like that's kind of like mixed, so that okay, so that maybe Alice got the horror one, so where she was paying A2, and then the Bob got the drama one where he was paying B1, and then the Charles would end up with the sci-fi one. So that is I just wanted to draw like a graph where like you would see kind of like the edges cross, so that don't make you think that, um, so this is like a potential solution, like, maybe if the numbers, depending on the value of the numbers, that could be like maybe the way you had to choose like who to sell what to. Okay, so this is like a potential solution. End result. But the reason why I'm drawing the graph here is that again, is to show you that at the end, once you make your decision, there should only be three edges at at the end of the process, because like everyone has to get something, right? So there should only be one connecting edge between a person and the corresponding movie that you get, right? So if, for example, if it were like 100 people with a different like different 100 movies that you could sell to them, there could be tons of different possibilities, because someone could be interested in buying 90 movies, another could be interested in buying 50 movies. So there could be tons of edges that you start with. Maybe you started with 500, like what is the most that you could actually have, like, like like maximum numbers that everyone is interested in everything, right? So it's 100 times 100 times 100 times 100 times like it's 100 to the 100, right? That's an insane gigantic like gigantic number, right? So you could start with millions of edges, and that's actually how networks like Instagram, like Facebook, I mean, you can imagine how easily this adapts to social media. You could start with millions of edges, but at the end of the day, in this assignment, you only, like, if it's 100 people, 100 movies, you had to draw at the end of the problem just 100 connecting edges. So like you are doing like an insane like amount of elimination, because again, like depending on like the preferences, like it is like an exponentially large number, and in the end you end up with something small, like, so that's kind of like to show you like the scope of what you're trying to achieve, like, uh, and so, and there's like a very cool way to solve this problem. And again, like what I would ask you to do on like in the exam is I give you like a graph and I ask you just to set it up. How would you solve it? Because like there's no point in kind of like solving it. Like once you understand what to do, like that's all that I care about. Um, what I like about this problem is that it also introduces binary variables, which are very important, like in computer science and in applications. So the question is, how do you set up this problem as how to set up this problem in terms of like an integer programming setup? So the trick will be to use uh, binary variables. So I'll do the following. Okay, so the first thing to do is that I will label the edges that I started with. So let me just Okay, so of course, like there's like not like a unique way to label them, but in this case, that's why I chose like alphabetical names, like, so that it kind of like obvious how you would call them. So for example, I could call this H1, this one would be H2, then H3. Like I'll use capital letters, actually, uppercase letters, so that to just to distinguish them a little bit better than from the amounts of money that you're willing to pay for them. Then H4, then H5, H6, and H7. Because in this case, like there were 7 edges, right? And then for each edge, I will attach to it a variable that can be either 0 or 1. So, in computer science, like or in logic, statements can only take two values, which are true or false. That's what a proposition basically is. So usually the truth value is assigned the value 1, and the false value is assigned the value 0. So for each edge, so step 1 is to label the edges. Let's put it as like an algorithm. Label edges. Step 2 is that you introduce a binary variable for each edge. Introduce a binary variable for each edge. Since there's 7 edges, I'll call them x1, x2, x3, x4, x5, x6, x7. Okay. And what is again, what makes it binary is that each of them can only assume two values, 0 or 1. Each of them can only be 0 or 1. And this is like the fun part. So when is it going to be 1? The value for the variable would be 1 precisely when that edge appears in the final, in the final decision, like in the end result. So if the edge happens to be when I decide, like, I'll put it in the diagram. But if I choose, if and if one of the edges is one that I'm actually going to use to sell the product, then that is like going to be assigned value 1. So xi equals 1 precisely when this edge is selected in the matching, like, for the matching. In the matching, and is 0 otherwise. So for example, just to show you what I mean of how this would work, like in this end result that I said, oh, this could have been like a potential end result, right? If this had been the configuration that actually ended up working the best, so what does that mean? That means that this was the second edge, if you remember. This second edge was selected, so that means that the value for this second edge would have been 1. Okay. Then what was the edge according with money B1? The edge with money B1 was E4, edge 4. So that was the fourth edge. So that means that the edge 4 would have value 1 as well. And what was this edge from C to S, from Charles to sci-fi with price C2? That was like the last edge. That was E7. So then that means that x7 would have been 1, and all the other values for the variables would have been 0 because none of the others were selected, and the remaining ones would have been 0. Is that making sense? Question so far so good. Kind of like the idea of like the variables. Is that making sense? So, okay. Okay, now comes like the cool part. Okay, so first, like, what is the function that you're trying to maximize? So let's like address that part next. So step two, it's step three, actually. Step three, what is the function? Well, so what I was saying is that, you know, should I? Yeah, yeah. So what I was saying is that what you're trying to do is like sell as much, make as much money as you can, right? So, and this is not the correct answer, but it's close to the correct answer. So you would think, oh, maybe what you want to maximize is A1 plus A2 plus A3, right? Plus B1 plus B2 plus B C1 plus C2, right? Oh, sorry, let me like write it in more space. I mean, this is kind of like the total amount of money you could make if like you got paid for all the edges, right? Like the point is that you are not going to be paid for all of them because you started with 7 edges, but you can only do 3 matchings. So, only three kind of can be activated at a time, And so kind of what I'm going to multiply is each of these quantities by the corresponding binary variable because kind of think of the binary variable as an on and off switch. So if the number, um, actually, I'll write it in the opposite order so that it looks better. So I'll do, it's going to look A1 X1 plus A2 X2 plus A3 X3 plus B1 X4 plus B2 X5 plus C1 X6 plus C2 X7. Because again, the idea is that these numbers, X1, X2, X3 up to X7 are either 0 or 1. So if one of them happens to be 0, that means that it doesn't contribute to the amount of money I'm making. And that makes sense because again, you cannot just add like all the amounts of money that you potentially you could have received because you can only choose 3 of the edges. So this is what the binary variables would take care of. Is that making sense? Kind of like the idea? Is that plausible? This should be the maximization function. Uh, so it's like a very elegant trick, but we're still not done because okay, this is supposed to be a linear optimization problem or like an integer program. So you have to have constraints or inequalities or something like that. So we somehow have to tell to the program that only 3 of the variables can be turned on at a time. Okay, and not like randomly because every person has to be assigned something and every movie has to go to someone. So all those conditions have to be incorporated into the programming. um so step 4, you have let's start first with the people. You have to tell the program that every person must go to like must receive a movie. Okay, every person exactly one movie. It's not more than one or less than, it's literally one movie. And then the trick for doing that, and this is actually how you model if you have taken like discrete math, how you model the OR operation in this type of linear programs. Because the idea, like let's look at Alice. Let's just start with Alice. So Alice was red, right? So what are the edges that come out of Alice? The red ones, right? A1, A2, A3, right? So of these 3, only one can be activated for Alice because if 2 are turned on, then she would have received 2 movies. So the way to incorporate that as a in kind of like this is very actually related to logic, but you know The way to force that to happen is by this. Because why is this enough? Because you're adding three numbers, right? The numbers are positive, they're like they're ones or zeros, right? So how are three numbers that add up to one, you know, how three numbers that are all either zero or one add up to one, where exactly one of them is one and the other two are zero? Is that making sense? Which is kind of obvious once you think about it, but like you have to kind of like be told at least for the first time before you realize, oh yeah, that's a good way actually. So this is one way of saying that of the three edges that Alice has attached to her, will become activated and the other two will kind of like remain off. Um, is it? I mean, it's kind of fun. I do like this a lot. Okay, how about, sorry, let's go to Bob. So Bob has edges 4 and 5 attached to him, right? So we want to activate just one of those two edges. So Bob, the condition for Bob would be that x4 plus x5 equals 1, right? And the condition for Charles would be, I mean, they're like the remaining two edges, right? If you look at Charles, they were edges 6 and 7. So the condition for Charles would be that x6 plus x7 equals 1. Is that okay? So far, so good. Everyone with me? Okay, so these three constraints guarantee that each person, from each person, like, they will only receive exactly one movie. But you still have to impose as extra conditions that the movies can only be sent to one that like the movies also like you have to do it for both the movies and the people. So you also have to say that the same movie cannot be assigned that multiple people, because this is just this guarantees that no person will be assigned more than one. This guarantees that one person will be assigned exactly one movie, but you also have to guarantee that every movie will be assigned exactly one person. It's kind of like not symmetric. So so now you have to say that each movie exactly one person. So now we have to look at it from the perspective of the movies. Well, I didn't put colors to these ones, but okay, let's look at drama. So which which are related to drama? So drama received edges 1, 4, 1 and 4. So one of these two has to be activated for drama, so that would be x1 and x4. Okay, so x1 and x4 has to be equal to 1. So that will guarantee that only of two of the edges that interact with drama, only one got turned on. Is that making sense? And then you go with the others just like that. Um, uh, horror. Horror had to do with edges 2. Okay, horror had 3. So it had to do with edges 2, 5, and 6. So 2, 5, and 6 have to be activated at least just at most once. So horror, 2, 5, and 6. And final condition would be the sci-fi genre, which goes to sci-fi. Sci-fi goes with 3 and 7. So one of these two must be activated. So 3 and 7. I don't know if you noticed, like in each of the partitions, like for the first set of people, like each variable appears once, which makes sense. Like like x1 is in one of the equations, x2 is you know, like there are no repetitions of the variables, and similar here, like, if you look at them, like the 7 variables are spread out among the equations, because it's like a way of saying that, you have to show up somewhere, because like like the edges connect the two vertices. So, but you cannot appear in more than once, because if you appear in more than once, then you would be connecting, like an edge would be connecting, like, two people with one movie, or two movies with one, that's like, same person. Um, does that make sense? And there you go. That's your integer program. So let's just write this all down. Like, so what you're trying to find is the max of a1 x1 plus a2 x2 plus a3 x3 plus b1 x4 plus b2 x5 plus c6, no, c1 x6 plus c2 x7, subject to what? Subject to these constraints, which I'll just write like, um, x1 plus x, I'll write them without the colors just to go faster. And each of the variables has to be 0 or 1. And then each variable is 0 or 1. And so that's an integer program, because like the values of the variables have to be integers, but it's even more specific than integer, because they cannot be 3 or 4, they have to be 0 or 1. So it's kind of like more, you could also call this like a binary problem, because like the variables are binary, take binary values, or like a logical problem, because it's kind of like, like again, like you can interpret like the values of these variables as was the edge chosen, and that's like a yes or no question. So whenever you have like a yes or no question, that's kind of like you know like represents a proposition. Basically, that's how you would call that in logic. Is that making sense? And then, well, now you can see why I would not ask you to solve this. Like already with 3 people, like you can have what? You have 7 variables and 6 equations, and kind of like at least you can kind of like see, you know, how it would go. So if in general, at least just to mention it, because in general, if the graph has what, n edges, then there n variables are n variables. So n is equal to 7 in our case, right? And if they are like, let's say, m, and if there are m people, there are 2m equations, right? So one equation per person, and one equation for the corresponding category that you're trying to match them with, be their professions or whatever. Again, like you could do this in many different problems. Another assignment problem could be like, you have 10 cities, you have 10 trucks, you want to ship your products to those 10 cities, like each truck must go to one of the cities. And then, like then you again think like you impose some condition, like, like maybe there's like a cost, that you have to pay for like like using a particular truck to a particular city, and then you have to minimize the cost, so like you would turn it into a min problem instead of a max. But I'm just saying, like, there are many variations of this problem, but hopefully it's easy to appreciate why it's like a useful thing to understand. uh just to finish this part, kind of like the cool thing, like the thing that's even more impressive, which the book does discuss, is that so what I was saying is that to solve this as a linear program, you forget about the condition that the variables are integers. So to solve it as a linear program, you relax it, The relaxation of saying that a variable is 0 or 1 is to say that the variable is between 0 and 1. So it's like just replace each variable to be on the interval 0 to 1. So the relaxation for a logical problem, like or like a problem that's binary, relaxation for a binary problem is just is to replace that the variable is 0 or 1 with uh that the variable is between 0 and 1. That's kind of like the uh best way to do the replacement in this case. And then you can you could apply the simplex method to that, but kind of, and that the book, I believe, does give like a proof, but it's like not enough time and not worth it. For this type of problems, like the cool part is that the solution that the simplex method gives, you can always produce an integer solution. Like, so, like the branches, like, there's no worries about like this branching stuff like can be avoided. So like you can always produce a solution with the simplex method that will give you already like integer values, which is kind of like surprising, like because again, like if you just think about it, once you relax the conditions to be numbers between 0 and 1, maybe one coordinate would be 0.5 or something like that. But what the branching, like what the book discusses is why in this very specific case, it has to do with like the fact that all the coefficients for the matrix are zeros or one. I mean, like it's like a very specific matrix here, the one that you're dealing with. But in this miraculous thing, let's see book. The simplex method can always produce like at the first step kind of like a solution with integer with binary values. The simplex method can always will yield whose coordinates are all binary. So like there's no need to branch basically. But for many problems, like like yeah, you do have to branch, but not for this particular one. Okay. And that also is why I wanted to mention this example, because sometimes it's kind of what you like I mentioned me earlier, like like the theory versus the practice. Like if you don't know much about the problem, you say, oh my God, this is who knows how many branches it would be needed in general. Maybe this like looks like for maybe you're super worried, and like for this particular class, it's just kind of miraculously there's no concerns. Like it all works perfectly. Like so sometimes sometimes like the way linear optimization works so nicely is because there are classes of problems where like the theory would make them sound very intimidating, but then the equations have a special features that kind of like makes it things not be as bad as they could have been. So um but yeah, but yeah, like something like the exam, I would just give you like a graph, and then I ask you like write like the function and write the equations that you would have needed to solve. But again, there's no more. I wouldn't ask more than that because you can already see this would take hours. I think if someone wanted to do it by like by hand, like like it's like a like 7 variables, 6 equations. So like like it would take a long time. So as I was saying, like next week will be the last week of classes, because then um, the last Monday of class, I will just do it like office hours. So the only thing that I want to mention, the remaining topic that I want to talk about is something also called Lagrangian relaxation, which is another way to relax these problems. So again, like one way to relax an integer problem um, is to just like what we were doing, where you just solve like the linear optimization problem by pretending that the variables are no longer integers. So again, relaxation is just like a way of saying making the problem easier. So that's one way to make the problem easier. Another way to make the problem easier, which is like this Lagrangian relaxation that I'll tell you about, is that you keep the variables integers, but you can like throw out some of the constraints. So in a clever way, so you cannot just like eliminate them, because otherwise that would not make sense. You kind of have to incorporate them into the function that you're maximizing. And I'll explain to you how that works, but it's like also like a cool idea. So, and this is like an also important method in practice. So, this branch and bound and the Lagrangian relaxations are kind of like two of the main ways people deal with these problems. And then I'll give you some applications. But yeah, that would be like the last topic that I would like to cover for the course, like how to do this Lagrangian stuff, because that's also related to like Lagrange multipliers if someone has taken multivariable. So it's like a nice topic also because of that reason as well. But let's end here and then I'll tell you about that on next week.